Hi, this is a presentation on standards for geospatial information and services. It's an overview of relevant standards and their implementation. My name is Doug Nebert. I'm with the U.S. Federal Geographic Data Committee. So why geospatial standards? Well, standardization lets individuals communicate with each other. It minimizes the cost of uptake of new information by learning to adopt a single view or format of things. It also maximizes the usability and stability of information products. Common or standard formats of information allow people to develop single applications that can operate under known conditions against a set of well-known or standardized behaviors, whether they're service interfaces or data format standards. There are three types of consensus organizations involved in geospatial standardization. In this case, we have ISO, the International Organization for Standards, that provide general purpose standards and guidance to their implementation. We have examples of industry consortia who provide technical implementation specifications, usually driven by industry and by the market. And finally, we have national or community groups that define common practices, content, and interaction within and outside the group. Typically, they focus on information content standards. Introduction to some of the examples of these. We have ISO has three relevant subcommittees or groups that have responsibility either directly or indirectly with the geospatial arena. ISO Technical Committee 211, 211, and TC 204 deal with geospatial standardization. 211 is geography in particular. 204 is with transportation and road transit in great detail. And Joint Technical Committee 1 has other standards of relevance such as catalogs and registries. The World Wide Web Consortium is another example of a voluntary consensus standards organization, as is the Open Geospatial Consortium or OpenGIS Consortium, OGC, and national standards bodies such as ANSI. So these different standards organizations play different roles, and they all work together in defining what standards you're going to select to apply within your community or within a spatial data infrastructure. ISO TC211 provides foundations for implementation. In general, they provide abstract standards, general standards that don't tell you exactly how to do things, but what some of the constraints are. The OpenGIS or Open Geospatial Consortium and W3C are much more practical standards, or in this case we'll call them implementation specifications, recipes for developers to know how to design and deploy software that works in specific ways. And the third group would be national standards. In the geospatial area, this is typically restricted to content standards or authority for data. But in defining the bounds of your spatial data infrastructure, you're going to want to select from the available standards that are out there, endorsed practices and specifications from ISO, from OGC, and from your national bodies. That makes sense. These then need to be communicated with members within the community so that you can have a higher level of interoperability both within your SDI and other SDIs. So in the case of the U.S., we can interact because of the adoption of the same sets of standards with Canada and Mexico. Countries within Europe can collaborate with each other in regional SDIs. And finally, we have a notion of a virtual global spatial data infrastructure, or GSDI, which is represented by the GSDI Association. There's a lot of interactions and a lot more detail. There are well over 100 standards that are relevant in some way to geospatial. We'll go through some of these fundamental relationships here and leave you with a list of current standards later. Over on the left we see the ISO organization and the three primary committees. Each of these committees has first-class liaison or collaboration relationships with each other. So somebody from the GIS standardization group, ISO TC211, will also be a liaison with TC204 for transportation, especially in the areas where we're talking about transportation data networks. And both would have representation and be able to approve or disapprove standards coming from the other bodies that relate to other standards within ISO. ISO is actually composed of only national standards organizations. A company cannot become a part of ISO, but a company can become a member of a national standards body such as ANSI or INSIGHTS or ASTM, and an individual can provide expertise in candidate standards from their organizations as approved by national standards. They can provide suggestions that their national standard even become an international standard. Their other primary role is to review and approve international standards for adoption in their country. ISO interacts with these other groups such as the World Wide Web Consortium, W3C, and JTC1. They have very similar kind of fundamental relationships. And the OGC is a Class A liaison with TC211. In fact, standards from the OGC can be fast-tracked through TC211 to be endorsed as ISO standards. In these cases, the document content is exactly the same, and it acts as effectively a cover letter that says ISO recognizes this voluntary consensus standard from OGC as an international standard. The adopter-implementer community then is going to have to sample from these different sources of standardization, like we mentioned before. This is typically done through facilitation bodies in different countries or regions, such as the Global Spatial Data Infrastructure. Within Australia and New Zealand, the ANSLIC. Within the Americas, there's the PCGIAP. In US, FGDC. In Europe, there's the INSPIRE. And in Canada, there's the GeoConnections activity. So these facilitation bodies can help establish a selected set of standards that are really your terms of engagement on SDI. Here is a subset of named standards that each of these bodies might be bringing to the table that could be selected by your implementer community within a country or region. Regional and state coordination groups can provide a forum for selecting and building a consistent network of solutions. They provide a forum for agreement on adoption of standards and practices that together really help function as a spatial data infrastructure. Without an agreement of standards, you really can't do things in an interoperable way. The GSDI, as mentioned before, is an initiative that seeks to promote these compatible SDIs worldwide. ISO TC211 has the objective to develop international standards for understanding and using geographic information, increasing availability of data and systems, contribute to unified approach to addressing humanitarian and ecological concerns, to ease the establishment of SDIs, and to contribute to sustainable development. Relevant standards from ISO include rules for application schema, which is the one used to define geography markup language. Basically says how do you take an abstract standard and turn it into something that can be implemented. ISO 19110, it provides a methodology for feature cataloging, for defining a data dictionary essentially for vector features. 19115 provides the international standard for metadata on data resources, and the companion 19119 provides a metadata standard for services. How do you describe and services so that they can be discovered on the web? 19128 is a web map service standard, also from OGC, and 19138 is a geography markup language, which also came from OGC. The W3C provides a lot of baseline definition of what it is to be the web. So the web has a certain level of architectural definition that everyone must agree to in order for it to work. Their level of standardization is called a recommendation with a capital R. That if you see a W3C recommendation, that's not just a suggestion, that's actually a standard. And we'll see in another page or two a list of familiar standards that they've contributed that should be regularly applied in a web environment. Here we see just a subset of W3C standards that could be relevant to geospatial, including things like HTML and HTTP for working with web and web pages, the PNG graphics standards, the ability to perform SOAP and web services interactions, the SVG for vector graphics, URIs and URLs, XHTML, which is an annotated form of XML and HTML together, and a variety of other standards related to XML. The OpenGIS Consortium, or Open Geospatial Consortium as it's now called, focuses on interoperability of software at the interface level to promote plug-and-play components for geographic interchange. It's a not-for-profit international consortium of over 220 industry, government, and university members. It focuses on the standardization of data syntax, data formats such as geography markup language, but has specialized in the definition of web service interface standards. Here is a sample set of OGC specifications, including simple features access. The items that are highlighted here in bold are probably the most commonly adopted within spatial data infrastructures. Catalog services are the standard by which one performs search against structured information, what we call metadata, over the web. So you can search on fields of data, such as the title, the abstract, the author, just like in a library, which is actually where this standard came from. Grid coverages is a specification for formatting raster or continuous field information and being able to query and access it. Coordinate transformation services are available. Web map server interfaces or web map services and web feature services are common data access standards. Geography markup language is a format of a dialect of XML, if you will. Filter encoding is a query format for geospatial information. A style layer descriptor is a way to format information from data into a view. So it's a set of rules that are applied to features that say, take everything that's classified as road class 1, make it red, double line width. Web coverage service provides access to those raster data sets. In terms of national standards, these are examples of standardization that occurs at the national level. Data content standards, geographic location gazetteer such as place names, geodetic reference systems, feature type catalogs or standard data schemas, national information profiles of international standards, such as an ISO standard that is received by the U.S., can become a national standard as well once it's endorsed. And finally, data policies and laws that are relevant within a national domain. In terms of data content standards, they help defining the meaning and the structure, or semantics and syntax, for information exchange for a specific theme of data. We have a number of standard application schemas that have been built for geospatial data in the U.S. and in Europe. These define a core or comprehensive packaging of spatial data, and by having a standard packaging of the information, it supports usage in OGC interfaces. This slide shows the value of having a common content model for framework encoding. If we encode data in the same way for the same theme, regardless of what software is being used, it can be transferred, imported, and exported from systems that may have a different native data format. This allows for each of the programmers of the systems to program just one interface for a specific type of data set that can actually interact with many other systems that support the same data model. Common ingredients for data standards. In this case, we're talking about framework or fundamental basic data sets that you would see in a topographic map. This would be identifying exactly what types of features or feature classes are included. If it's relevant, having a unique feature identifier system for, say, a segment of road, a piece of river, a parcel, so that it can be found and reused and, more importantly, joined to tabular statistical data sets. You would define what the basic attributes and their properties are, what data types they are, and any authority, whether there's a controlled vocabulary of codes for some of these attribute properties, whether a given data set was valid or restricted to a certain range of scales and resolutions, and to, wherever possible, support multiple representations of the same features at different scales. So having multiple geometries for a real feature in the real world. Again, a road exists once, and yet it can be represented in many different ways at different scales and different periods of time. By having a common identifier for that segment of road, and it allows us to join up multiple representations or even multiple references. Another symptom or feature we see in national spatial data infrastructures is to establish web feature services on agreed content nationwide. So again, where mission system A and B in this example have different native formats, different way that they're storing the data in their database, it can be transformed or translated from a private schema, that which is in their native format, to a public schema, which is the one referenced by the standard. Basically converting the data, repackaging it into an identical format that a client, whether it's a web feature browser or a client application, can use. So in this case, coming out of the web feature services, there are two of them here, would be the exactly same, identically structured GML or XML data coming out. So once more, the client application would need to only know how to understand one format of data from different systems. Another area of standardization in a country is a geographic location, gazetteer, or place name database. These are named places. They can be different kinds of features, like a location or a school, a district administrative unit. But typically they include a first and second order subdivision. First order may be a province or a state. Second order could be a district or a county. They include populated places and named landscape features. Establishment of an online gazetteer service by each nation is also useful. That way people can query and retrieve places and coordinates and properties. This can be used by web map interfaces, web service interfaces, to help you with locating things by place. There is a gazetteer profile of the web feature service that allows for resolving geographic names and identifiers. It's being developed to query geographic name servers, so you can do place name lookup and coordinate assignment. You give it a name, it gives you back coordinates. Metadata collection can benefit from access to web service to encode place as name and coordinates. So when you're collecting information about a location in a data set or a named watershed, you can go to a gazetteer service and get things like watersheds or cities or counties and get the coordinates that define the boundaries of those features. You can paste those back into your metadata, so to speak. And by having these gazetteers, it can support geospatial search. So the gazetteer interaction then, an application with a user then asks for, I've got a Clark County, Nevada. It's a place name to the gazetteer service and may get a result then in a structure that would include the place name and its state, but it would also include the spatial coordinates, either as a point centroid, a bounding rectangle, and or a bounding polygon. Geodetic reference systems are another means of national standardization. One can select and conform to some national horizontal and vertical datum. This is important for placement, especially as the precision of GPS is increased and surveying tools increases over the years. So having something that's within centimeters or millimeters of location is more important, and it's absolutely essential to have common geodetic reference systems adopted within the community. So standards are established to adopt horizontal and vertical datums. Feature type catalogs can also be published as standards within countries, basically saying I have a class of a feature, such as water features, hydrographic features, which would include streams and rivers, ponds, lakes, reservoirs, things like that. And each of those would have a definition, an authority, who defined them and how they get defined, and what relationships those feature types might have to one another. ISO includes a feature cataloging methodology to help in building these feature type catalogs. National information profiles of international standards can be built. Essentially, any ISO standard will be sent to member countries to be potentially adopted by those countries as national standards. But in effect, they're actually national profiles of international standards. These profiles can allow for clarification or localization or even extension of the ISO standard, so they become adaptations or local permutations of international standards. Examples of standard profiles of ISO include metadata, feature catalogs, and application schemas. And at the national level, you may also have data access policies on governmental and private data. You usually need to review existing information, technology, legislation, and policies and see if there's some geospatially relevant tact you need to take to establish data exchange policies and the understanding that governmental data providers have some obligations to address privacy, intellectual property, and security issues, and to define the terms of participation within the national SDI environment. There's really a lot to choose from. Standardization should be a least cost means of establishing a common means of interaction between participants in a process. So it's the least amount of standardization you need to achieve the maximum amount of interoperability. Community facilitators then, and facilitation organizations such as FGDC and other equivalent national and community bodies, really play a critical role in building consensus on adopting standards and building an architecture based on requirements, and then define what those standards, specs, and practices are in ways that people can understand. So this forms a blueprint for a spatial data infrastructure. These standards for, say, ISO metadata to include feature catalogs, to have data content standards for specific and popular data themes, to encode the data on the web, such as using GML, and to adopt a small set of web service specifications that everybody in your SDI should be deploying. So here we can see in bubbles or clouds the kinds of standards that inform each of these elements in blue. Data is produced, metadata is produced according to ISO 19115. Data is described using an ISO feature catalog. It may be harmonized with national or international data content standards. These data are then provided through data services, which are standardized as OGC catalog services and web map and web feature services. They are made available then over the internet using standard formats such as GML and XML and KML to the end user. So there's opportunities, needs and opportunities here to inform potential adopters about the standards and their implementation, promote an architecture, to build and share common feature catalogs, content, and data exchange standards for features and files on the web. All of these players are factors within the development of a spatial data infrastructure within that community, which is your NSDI community, and in defining a blueprint for coordination. So another way to look at standards to be aware of, there are standards associated with data, your national standards in particular. For access and discovery services, you need to think of OGC catalogs and ISO metadata. For applications and models and interfaces between and feeding those models, you would like to describe your data content using rules for application schema, the ISO web mapping service, or OGC web map service, and the web feature service. And from a portal or a project perspective, you generally want to adopt OGC and W3C web services, gazetteer services, and the ability to perform service chaining. Here's a current set of candidate SDI standards defined earlier this year in 2009. We see the version number next to each one of these on the screen. So somewhere within a national spatial data infrastructure you would see all of these standards being implemented in the appropriate place, whether it's for serving maps, for discovering information, for serving data, or accessing data, or portraying data.